Hello everyone. So today we'll be starting a new algorithm series, and we'll be covering like dynamic programming. So in this series, the first problem is climbing stairs. So it is one of the easiest yet one of the best to understand how a dynamic programming works. So let's go through the problem. The problem states that you are climbing a staircase and it takes n steps to reach to the top, right? So there is a stair and n, a given number, and n represents the number of steps. Each time you can either climb one or two steps. Either you can go one step or you can take two steps. And the question is, in how many distinct ways can you climb to the top? Okay, so the problem is straightforward, that we'll be given a number that represents the number of stairs, and we just have to calculate how many distinct ways we can reach to the top by taking one or two steps. So let's draw a decision tree for this particular problem. So let's n is the number of staircase. Let it be 3. So we have one stair, two stair, and third stair. And our guy is starting from here, right? And from the 0th position, from here, he can go to either one step or he can go to two steps. So at every step he will have two choices, either one step or two steps. So keeping that in mind, if we draw a decision tree, it will look like this is the guy starting from 0th step. Either he can take one step or he can take two steps. So if it takes one step, then the number of steps becomes 1. Here the number of steps become 2, right? And from here he can take again one step or two steps, right? If he takes again 1, the number of steps here becomes 2. Here the number of steps become 3. So now we reached the third position. So this is a possible route, right? We get one route. Now here, after he takes two steps, either he can take one step or he can take two steps again. So this will become 3 and this will become 4. So since the 4 is greater than our third step, so this is invalid. But here we again reached at the top. The time we reach the top, so this is again a possible way, that is 2 and 1. He can get 2 and 1, and here in a 1 and 2, so he can get 1 and 2. Here again he take 1 or 2, so this will become 3, so this will become 1 1 1, so 1 1 1 1, so this is also become another route. But here if we take 2, this will become 4 and this is invalid. So we, in this decision tree, we get 3 routes, like 1 1 1, 1 2 1, and 2 1 2. So total number of distinct way is 3. But here since the number of decisions is 2, right? So here what happened here, like it will create 2 to power n order, the order of it's like OF 2 to power n. But we can optimize it because we're going to 2 here, again we're going to 2. So once we calculate 2 and second time we go to 2, we can use the last one, and by memoization, so by using memoization we can optimize it and increase the performance. But again, this can be solved using a dynamic programming. So how we can implement dynamic programming here? So by the time, if we start from reverse, like let's see if, just imagine that this guy is starting from the top, right? So now if he starts from top at third position, the only way he can reach a third is 1. Same, it goes to second position. From here he can start, it's only 1 because he cannot take 2 steps, so 1. Now when he goes to first position, what happened? Either he can go to 2 or he can go to 3. So if he go to 2, how many ways he can do from 2? That is 1. If he goes to 3, how many ways he can do from 3? 1. So total will be 2. So now from 0th ground, either he can go to 1 or he can go to 2. So if he goes to 1, the number of way he can do is 2. If he goes to 2, the number of way he can do is 1. So total is equal to 2 plus 1 equals to 3. So we have to just keep adding the previously calculated 2 steps to get the possible steps, and this will become our solution, and it will the order of operation will become OFN. So we're gonna implement both. First we're gonna implement the decision tree, and then we'll be implementing the dynamic one. So on the screen I have created the functions for both. So let's create first the dynamic one. Let's create a function calc steps, and that will take our step, and then now in calculate step, in every, so 2 decision we have to make, right? In this base cases that we decide if our step equals to n, means if this is third step and we already reached at the third step, then we just have to return 1, means we return that we found 1 way. If not, if steps is greater than n, we just have to return 0. It means we don't have to you don't have to we don't have to calc, because that is not a way. So we have to say that, okay, that is not a valid path, so we have to return 0. And the final path we just have to return like calc steps one step, like step plus 1 plus calc steps plus 2, right? Now we have to return calc steps starts from 0 step. Okay, so this should do our calculations for, so the 2 base cases are there, and then we calculated 2 decision decision path from that particular, from every step. So let's see if how our test cases goes. We go there, this is our test case. Let's return recursively, and it passed. Okay, now let's try to optimize it. Okay, because we just have to keep track of the steps that we already been calculated before, and we in the decision tree, if we come across the same step, we'll see whether we have calculated it before or not, and just return the value. For that, we just have to like implement a map. Let map equals to new map, right? And then in this particular case, rather than returning directly 1, we're gonna first save it to the map. So map dot we're gonna step 1, then return. Same way we're gonna do here as well. So map.set, we're gonna say step and 0, then return 0, and at the top we're gonna return if map.head step, then return map.get step. So this should optimize our solution. So now let's go and check our code. And there we go, it passed. So first we implemented our recursive decision tree, then we introduced our memoization to make it a little bit efficient, and now we're gonna try our dynamic programming. So now let's solve it using our dynamic programming that we described in the whiteboard, right? So to implement dynamic programming, first we need to create an DP array, right? Array, let's call it mem. So let mem equals to array of length plus 1, because we're gonna create one element more so that we can cover the ground floor, the ground where the steps begin, and then we're gonna fill it with 1. I filled it with 1 because the last 2 steps will always stay 1, so we don't have to do anything for those. Now we're going to write a for loop for let I equals to n. Since we started n plus 1, so total length, the last index will be n plus 1 minus 1, that is n. And then let I greater than equals to 0, then we're going to do I minus minus. Okay, so here our array will look like, for if the n is 3, it's going to look like 1 1 1 1, right? Now the length, the last index is 3. Now we're going to write the if condition if our I is, when we come to this index, until we get this index we don't have to do anything. So I is greater than 3, that is what, 0 1, right? 0 1, so 3 minus 2. I'm sorry, what I'm saying, n, sorry, I is greater than n minus 2, right? N is 3, 3 minus 2 is the last one. We don't have to do anything. Continue. Else we have to do the sum. So mem of I equals to mem of I plus 1 plus mem of I plus 2. And at the end, in this particular case, what's going to happen is, like, it will become like 3 2 1 and 1, right? So at the end we just have to return the mem of 0, and this should solve our problem. Let's see how our test cases are doing. So these are the test cases. I'm running those again. So boom, our test cases has passed, and this is how to solve this staircase problem in different ways. So thank you so much.